Hello, welcome to our video series giving us solutions to Superquiz 2 from my Spring 21 Math 250A, which is Calculus 3. Let's see, so this first video solution, we are trying to find and classify critical points for a function of two variables, given here as follows. So when we say classify, of course, this means determine which of the critical points is going to be a local minimum, a local maximum, or possibly a saddle point. So, of course, our goal here is basically find the critical points and then use the second derivative test. So this is our sort of our two-step process, right? Step one, find the critical points, and step two is use the second derivative test, which really means use the Hessian to evaluate or classify the critical points. So to classify here the critical points. All right, so to find the critical points, we're going to compute the gradient of the function f and set it equal to 0. Any points where the gradient is either undefined, which won't be an issue here because we have a polynomial, or where the gradient is 0 are what we call critical points. So let's move down just a teeny little bit. There we go. All right, so step one, we're going to find the critical points. So we compute the gradient, which means we're going to compute the partial with respect to x and the partial with respect to y. And so the partial with respect to x will be 3x squared. Okay, the y cubed is a constant, so that doesn't do anything, minus 3. And then the rest of this is a function of y, so it's a constant. Okay, now we take the partial with respect to y, and we'll get 3y squared minus 12. So we want to know where does the gradient equal 0. Well, that's going to be where each component equals 0. So 0 is 3x squared minus 3, and 0 is 3x squared minus 12. Y squared, excuse me. So the top one, let's see, we can solve for x squared, add 3, divide by 3. So add 3 and then divide by 3, and you'll get x squared is equal to 1. And so x is plus or minus 1. And in the bottom, you add 12 and then divide by 3, and you'll get y squared is equal to 4. And so y will be plus or minus 2. So we're going to get critical points when x is 1 and y is 2, or x is 1 and y is negative 2, negative 1, 2, negative 1, negative 2. Right? There's 4 critical points. So we have 1, 2, negative 1, 2, 1, negative 2, and negative 1, negative 2. So we're going to have to classify all 4 of these points, and we're going to move to step 2 now, where we compute the Hessian in order to classify those points. So remember that the Hessian of f is going to be the partial with respect to x, right? So it's like it's a second derivative both times with respect to x, times fyy, minus, now you do the mixed partial. You take the partial with respect to x and then with respect to y. And of course, we're using Clairaut's theorem here to know that we don't have to multiply by fyx. Instead, we can just square fxy. So in this case, let's see, since fx is 3x squared minus 3, if we take the partial with respect to x again, we'll get 6x. Okay, so that's our fxx. And then this was over here 3y squared minus 12, the partial with respect to y. If we again take a derivative with respect to y, we'll get 6y. Minus, all right, now we go back to fx and we take a derivative with respect to y, but now there are no y's here. So with respect to y, this is a constant, and so the derivative is 0. And then, of course, we can square 0. And so in total, we get 36 times x times y. Okay, so now we're just going to compute the Hessian at each of our 4 critical points. So at 1, 2, we'll get 36 times 1 times 2. I'm just plugging 1 and 2 in for x and y. And okay, it turns out this is 72, but I don't really care what the actual value is for these purposes. I just care that this is going to be something positive. Now, once I know that I have a positive Hessian, okay, so a positive Hessian, I know I'm going to get a local max or min. And it's just a matter of which one it is. And the way we can determine it is by looking for the concavity in either the x or the y direction. By convention, we always seem to do the x direction. So let's check that concavity. So I get the concavity in the x direction by checking the sign of the second partial derivative. So at 1, 2, fxx, well, we know that was 6x, right? I should mark that. That was fxy. Fxx 1, 2 is equal to 6 times 1. Right? Our x value is 1 here. So 6 times 1, which is again positive. So this tells us that we have positive concavity in the x direction at 1, 2. Now positive concavity, right, that looks like this. That means you're getting a local minimum. Okay, so the positivity of fxx tells us we have a local min at 1, 2. Okay, let's check at negative 1, 2. So in this case, the Hessian will now be 36 times negative 1 times 2, which is now a negative number. And once you get a negative number, you don't have to check concavity or anything. A negative Hessian always implies that you have a saddle point. So we'll have a saddle point at negative 1, 2. All right, how about at 1, negative 2? Well, now we'll have 36 times 1 times negative 2, which again gives us a negative Hessian. So again, we get a saddle point. How nice. Okay, last critical point, negative 1, negative 2. I feel good we're not going to get a saddle point again because now we have two negatives. Okay, so we're going to get a positive. So positive Hessian again implies we have a local max or min. So we're going to want to check the concavity in the x direction, say. So we'll look at the second partial derivative in the x direction. And this is now going to be 6 times negative 1, which is a negative number. This tells me I have negative concavity, and so I must be getting a local maximum. So we get a local max at negative 1, negative 2. All right, so let's see. We found 4 critical points. We've determined one of them was a local min, one was a local max, and the other 2 are saddle points, and so the classification is complete.